Okay, it's 3 o'clock. Today, before I start class, um, you should have received an email about evaluations for this class. Right. I will give you 10 minutes to fill that in now. Please do that now. You can do it on your phone. You can do that on your computer, but do it, all right? Because the school takes it seriously and I do as well. So fill it in. And then I can't be here when that's going on. So I'll be outside. I'll come back at 3:10. Uh, just use this time to do that, okay? So you can access it on your phone. It's on Moodle, it's everywhere. So just use this time to fill that in, all right? Okay, thank you for doing that. We will finish this chapter today. Um, and I think essentially we've done the class. I will also be showing you the movie, so if you want to fire that up, yeah, right. You do? That is such a positive thing to hear. Because, but I must say, I've not actually heard students say they hate it. So
No, the movie's fun.
good. I like the graphics it makes. I honestly,
It's easy to use, you know. It's like makes sense.
right.
Streamlined.
So we will be using Jamovi in a minute. Not just yet. I want to very quickly review where we came from the last time. Um, so we were looking at a foot length and height data set, if you remember. Let me just check with you guys. When I say you, I should stop saying you guys. Let me check with you all, right? Let me check with you all. Uh, which variable did we pick as the explanatory? Do you remember? It could go either way, but what did we choose?
Oh, sorry. I thought you were. I was gonna say it can go either way.
Yes, it can go either way. Do you have? But do you remember? Do you remember which we settled on in this class? Yes, you're right. It was foot length. We are using foot length to explain height. Good, right? That has to be established first, although it could go either way. All right. So the key thing is that this data set has both variables quantitative. You represent that kind of data on a scatter plot. All right. We then started our discussion a little bit on drawing a best possible straight line. All these things I'm going to show you today in the movie how to get. Right? How do you get a picture like that? Right? Now, and we did define, there are a few definitions of best. If you remember, when people say you're the best, it can mean all kinds of things. That's also the same for lines, right? What's the best line you could draw? Can anyone tell me? This is not easy. Let me straight up say, what criterion for best have I adopted? Do you remember from last week? I know 5 days have passed. Do you remember the criterion for best, which I use? Yes.
And the best line is the one that minimizes the total square distance between all of like the dots.
Yes, thank you. Right? Exactly. So what do you go by Josh? Right?
Yeah.
Okay. Some people don't, so I just want to check. Okay. So the line, my best line definition is the line. And why am I saying the line? Because there is no other line like this. There's only one. Yes.
Is there a certain number of like square where it's not close to the line where you can't count it as a line of best fit?
Come again? What are you?
So like, is there like, at what point is there not a line of best fit? It's just random.
That is also a very good. If you give me a scatter plot, I can always find you the best one, and there's only one.
Okay.
It could be it. I think what you're asking is,
Even if it's random?
even if the points are random, it is always possible to find the line of best fit. It will be a very stupid line to draw.
Yeah.
But you can, and it is also unique.
Okay.
Okay, that's a very, very good question, actually. So what Christian is asking is, what if your lines were like not like this, like really all over the place? Can you still find a best line? You can. Because can I still minimize the spread distances to the line? I can. It's just that it will be high. That sum will be big, but that doesn't stop it from being the best line. It's kind of like in a class where everyone did very badly on exams. Will someone still be the best? Right? Let's say everyone got less than 20% on an exam. Someone's got to be the best anyway. And I think that kind of, yes.
I guess, I mean, not so much is if it's possible to write it, but like, you know how it's like if your histogram is skewed, it makes it like you're not allowed to use that.
Oh, that is again a foreshadowing of where we're going. So you're saying, is there some criterion that you look at before you start saying, I'm not going to draw a line anymore? Is that clear?
Yeah.
There is, and we're coming to that.
Okay.
Very good. All right. Okay. What Christian is asking is, what if the points are a sea of dots with clearly no line pattern? Is there a way to indicate that you shouldn't be drawing a line? Yes, there is, and that's a very, very good question. We will also get to that. Right? One sign that the class is tracking you is that they are asking good questions, so that's excellent. So you also know that A line comes with two things that identify it. One is the y-intercept. I'm not going to go into the whole story about what symbols Americans use and all that. Just know that in statistics, the y-intercept is symbolized by little a, and the slope is symbolized by little b. We ended last week by talking about two things. Can you interpret 38.3? There was some hesitancy. The class was not so willing to tell me because it seemed to make no sense. 38.3 is the predicted, see the head? It's the predicted height of someone whose foot length is, give me a number. 38.3 is the predicted height of someone whose foot length is, yes, good. Right? Be brave. That's right. That's the mathematical statement. If your foot length is 0, then this is your predicted height because this is a 0. So this has no practical meaning. It only has a mathematical interpretation. It has no practical meaning. No one has foot length 0. The harder one was interpreting 1.03, little b. Does anyone want to try? 1.03 is the predicted rise in height for a, what's the, sorry? For every unit increase in, good, for every 1 unit increase in which variable? 1.03 is the predicted rise in height for every 1 unit increase in foot length. Very good. Excellent. So make sure these things are copied down in your slides. All right. I want to talk about something immediately. Yeah. Okay. Everything I've just said is here. In fact, I took away the word 1 unit increase. I did say 1 centimeter. I'll explain. I didn't show you the data yet, so you didn't know it was centimeters. The unit here was centimeters. And do you notice something kind of strange? The height is measured in inches, but the foot length was measured in centimeters. It doesn't matter. You just have to be careful, that's all. It does not matter. It doesn't mean that they both must be the same unit. Is this okay? After all, can't I predict something else, not height? Can I use foot length to predict your weight? I could, and weight and height are not measured in the same scale or unit. So it doesn't matter. All right, you can have inches for your height, centimeters for your foot length, and vice versa. It doesn't matter. That's why in my description of a slope, I said for every 1 unit increase. That's generic. But if you know the unit, put it in. All right, so everything I just talked about is in this slide. All right. I will now show you how to get these things on Jamovi. All right. So I will return to this slide, but I'll give you a few more seconds to finish copying this. Then I'll go on. All right. First of all, where is the data? Okay. First of all, the data look like this. If you went to our Moodle dataset, sheet, go to the foot length and height tab and go look for that one. Foot length and height. I want you to stare at these numbers a bit. Are you comfortable with this kind of data presentation? These are people's foot length and their corresponding. Every row is one person. All right. So can you tell that the units are different? First of all, would it be sensible to have foot length in inches? Always do a check, you know. Right? Even though you're in a stats class, you should imagine you're in a chemistry class or something. I know chemistry students, especially physics, chemistry, these two sciences, they really make a big deal about units and dimensions and decimal places as well, which this class is more lax on. Right? If you try reporting something with 6 or 7, you probably get a scolding, right? But anyway, the point is, this is a math class, so I don't care. Foot length and height. How do you know that foot length is in centimeters? Because inches would be crazy. Who has 30-inch feet? Right? In the same way, this cannot be cm because who is 67 cm tall? So always do a sanity check and look whether your numbers are even making. But the point is, first of all, you can have different units. It doesn't matter. You just have to be very careful when you interpret your slope. You have to talk carefully. Predicted rise in height in inches for a 1 centimeter increase in foot length. That's the only two unit systems that make sense. Okay. Okay, so let's Jamovi now. Let me show you how this works in Jamovi. So follow what I do. Select, remember Jamovi has this thing, you don't select, do not select the words. Just select the data and you'll thank me later. So go to Jamovi and paste. Okay, go paste the data like that, like what I've done. Okay, now comes some important steps, which again, if you don't catch everything I say, I have a video. I think I've talked about this video so much. I have a video that teaches all these things. Now, do you realize something has happened? Is Jamovi smart? Has it detected that column A is numbers? You see a ruler? The ruler appeared. But did you see that for B, it wasn't smart enough? Did you see that? I think it's because B has no decimal. Oh yeah, B has no decimal points. So it thought that those are tags. So what do you need to do? Change it. So this is very important. You don't want those circles there. Double click. Measure type, not nominal, but continuous. Ruler. Change the name to something meaningful. You will thank me later. What variable was this? Foot length or height? Which is this one? This is height, right? B is height. Height.
Yeah.
Okay. And then come out. All right. This was ruler already, but I will change the name to something more meaningful. Foot length. Okay, very good. Do that first. Before anything else, do that first. Now, I think in order of presentation, I'm going to teach you how to get a scatter plot first. There are no statistics yet. Okay, anyone have any guesses? Exploration. You want pictures? Exploration. Scatter plot. Is that easy? So you can make a note in your slides. Exploration to get scatter plot. Paste data. Change to ruler. If you want to write it that way. Paste data. Change to ruler for both. Exploration. Scatter plot. Okay. When you see this, well, what goes into x-axis? Anyone? Which variable? Foot. Good. We are choosing foot length as our explanatory variable. It could go either way, but we're fixing it as this one. Height goes into y-axis. Was that easy? I really don't know what could be easier. Right? That's why Jamovi is a nice thing to use. The plots are lovely too. Much better than Excel or Google Sheets. It's nice. Okay, so that's your plot. All right. Do you want a regression line? Do you want the best least square regression line? Do you see regression line linear? Okay. Don't want the line? Hit none. That's it. That is it. Okay. Okay. So now let me show you how I got this in the slides. Let me go back to my slides. Did you wonder how do I get this table? How do I get the 38.3 and the 1.03? Well, I'll show you now. It's not very much more difficult, only slightly. Can you guess? You go to analysis, regression. So you can write in your slides, analysis, regression. Do you see linear regression? The word linear line. Okay, click on that one. So regression. So one thing to know about Jamovi is there's two tracks. You want pictures, you go to exploration. You want analysis, you go to the analysis. Actually, there's on the analysis tab. Go to the correct model. All right, so go to regression, linear regression. Okay, just a few things. I think the easiest thing to teach you first is what's the dependent variable. Dependent variable is another name for, what's the word we use in this class? The dependent variable is also known as the AKA. Yes, the dependent is the response. Don't mix them up, right? The dependent is a response. Who's the response in our case? Height. Good. So push height in. And now the only thing is, again, I don't know why they like to use all these kinds of words. I mean, there is a reason, but it's beyond this class. Go to the covariate box. Covariates is the explanatory. I'm sorry, there are these terms to know. You must know this. Covariate stands for the explanatory variable in our context. So foot length will be pushed into the covariate slot. Did you see that? Immediately, do you see that the T table that I have in my notes has appeared? Right? There it is. 38.3021. Somehow when I made my slides, I asked for 2 decimal places. Does that disturb you? I hope not, right? My current Jamovi has 4 dp, so fine. Is this okay? That's how you do it. Do you see the 1.03? Do you see 38.3? Okay. Okay. And that will be it for now. Hold on to this page. We will revisit it. All right. That's all I want to do for now for Jamovi. I always believe in doing things gradually like this. Okay. We can use the prediction equation to predict heights of people. This is the first use of the prediction equation. What do I mean by the prediction equation? Can you write in your slides in big bold letters? This is the prediction equation. This one. Height at equals blah, 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 blah. That's the prediction equation. Why? Because it predicts things. It's called the prediction equation because it makes predictions. It predicts your height. So that's the PE, all right? That's the prediction equation. How do you use it to predict? I hope this is obvious. How do you predict the height of someone whose foot length is 31? Well, put 31 in. Do you see that? Where foot length was, put 31 in. And then always check whether the answer given computes. Does it, what's the word that we want? Does it make sense? That someone whose foot length is 31 centimeters is predicted to be 70 inches tall. Does that make sense to you? Yeah, it does. So the model is doing something reasonable. Always do that. And that is one classic way to check whether your units are correct. Because if you're getting something crazy like 700 inches or 7,000 inches, that means you probably have a calculator issue. All right? That's how you tell. Okay, here's something. I had a professor in grad school. I'm not like that. He would actually take points away if your answer made no logical sense. He would actually do it. Right? He was one of a brilliant professor in my grad school. His exams were so hard, and he taught not just grad school. You know, he didn't just teach me as a graduate student. He also taught other graduates. He taught an intro stat class. I tell you, those students really died, right? Because he made the intro stat class so hard, right? Because he's just so clever and so good, and the students in the class was so far away from where he was, like planets apart, right? So you can imagine. But anyway, yeah, he was not well liked, this professor, right? Very smart, but not well liked. All right. Anyway, what is the residual when we predict the height of someone? Okay, I'm going to teach you a definition now, which is what is a residual? Actually, the English word residual, what does it mean? Does anyone know? What does a residual mean? Yes, perfect. It's what's left behind. Yes, the residual is what's left behind. So the definition of the residual is actual minus predicted. Please write that down in huge font size 25, right? Because this is a very important definition, which is all the way, whatever stats class you do, no matter how high level, the definition of a residual is always the same. Actual, real height minus prediction. It's not, it's the disparity between what you observe and what you predict. Is this okay? Disparity, difference between the actual thing that you got versus what the model predicts it to be. So, if a model is good, should the residuals be small or big? Small. That's it. All right. So, do you understand why the residual for this person is negative 0.13? Follow the definition. We predicted first that this person whose foot length is 31 centimeters would be predicted to be 70.23 inches. That's a prediction. That's what the model says. But the actual height was 70.1. This person's real actual height was 70.1. So the model did a pretty good job. It's quite close. The residual is not even an inch. So it's actually doing a good job. Yes.
What would be considered a bad job?
Oh, that's relative to the problem and the site. So that's a question answerable by computing what's called the mean square error. So you look at in general how big are your disparities, and then you compare it to other models. So the absolute size of the error is not so much of concern as in the relative size of the error when you compare to other models. Again, excellent question. Is this okay? All right. So don't be alarmed by the negative sign. Some residuals are negative. Because if what you predict is slightly more than what you saw, you're going to get a negative number. That's fine. And please, for homework problems, for exam, if it's negative, please report negative. Don't say, I'm going to take the positive. That's an important point. Don't positive it, right? If it's negative, it's negative. That's fine. All right. We need to be cautious if you plug in values of foot length that are outside your original data range. Doing that is called what? Now, I'd be very happy if someone knows what this word is. The act of plugging in values of foot length that are outside what your data had. There's no, let's say there's no one in the data set with foot length more than 35 centimeters. If I use the model to predict on someone whose foot length is 36 centimeters, what is the act of doing that called? One word, pretty long. Anyone know? Give you a hint. It starts with an E. Long word. The act of plugging in data that is outside your range is called. Yes, it's called extrapolating, and the process is called extrapolation. Very good. Good. I've had quite a few classes that couldn't get it, and I do the whole Wheel of Fortune thing. Okay, now I give you an X, then I give you a P and all that. Okay, it's kind of embarrassing, but we didn't have to do that. So this is called extrapolation. The moral of the story is this: extrapolation can happen. The equation will work. And that's the dangerous part about statistics. The equation is not going to hang. It's going to work. It doesn't switch off or zone out or time out, or it works, but you shouldn't be doing that. See, it's one of those, can you, yes, should you, no. Or if you are asked to extrapolate, protect yourself by putting a disclaimer, put an asterisk. This is an extrapolation. Do that. Right? Just like when you send an email, what's the CC field for? Yes, the official reason is you want people to also know but don't have to respond. But when you work next time, trust me, the CC is used to cover yourself. Anyway, so it's very CC, cover, can't think of another C, right? Cover all your bases, maybe. Okay. But basically, if you are asked to do an extrapolation, protect yourself, say, hey, hello, this is an extrapolation, okay? I'm giving you an answer, but take it for what it's worth. Okay. So what do I mean? Can I use the prediction equation to predict the height of someone whose foot length is 100 centimeters long? Is the equation going to work? Yes. Equations always work. Can I predict the height of someone whose foot length is 1,000 centimeters? Yes. The equation will not blow up, but it's becoming ridiculous. So you should not do that. All right. That's called extrapolation. The equation works, but these kinds of predictions must be treated carefully. All right. So so to answer Christian's question, is there a measure of the strength of the linear relationship between two variables? That's precisely what he was asking. Like, is there a level of weakness when the dots are like stars in the sky with no pattern anymore, should you even be fitting the line? There is. This measure is called the LCC, the linear correlation coefficient. Right? The linear correlation coefficient, LCC. The word linear is very important because many people drop it. They always say, what's the correlation? Correlation can exist in many forms. You can have a curved correlation. You can have a circular relationship. Please say linear. It triggers me no end when people read out the word L. It's a linear correlation coefficient. It measures how strong the linear relationship is. Right? It's symbolized by little r. I don't know why. I don't know why r. I really don't. All right? Little r. All right? It is also obtainable from Jamovi. Where? Okay. So, do you see R? Okay, I know Jamovi uses capital R. Uh, there is a reason why they do that, but technically it's wrong. It should be little r. They did it because you do get r from square, taking the square root of r squared. They wanted to be consistent between the two, but the symbol for r, the LCC, is little r. No one uses big R. Right? It's a fine point, but never. So do you see 0.7114? There it is. The movie gives it to you even without you having to ask for it. This number is the LCC. Remember that. What's R squared? Coming to that. Right? These two are related, of course. One comes from the other, but they mean different things. The strength of a linear relationship is measured by the linear correlation coefficient 0.7114. All right. So what values can that thing take? So first of all, you will notice that the value for R has a sign. It so happens in this case that this was positive. You can have negative LCCs. Just please note that. If you want on your slides, you can put an arrow there. This one's positive, but can be negative. Yes.
Is it negative just regression?
Yeah, a negative. Okay. When will the LCC be plus? Anyone have any guesses? Actually, I think it's on the slide. When is the LCC value plus? It is a positive value if the linear relationship between them is a positive one. For example, foot length and height have a positive relationship, right? When your foot length is bigger, do you get taller in this data set? Yes. That's a positive relationship. And so the value of the sign of R reflects that. A negative value R tells you that the relationship is a negative one, like car price and car age. As the car gets older, it's worth less. That's a negative relationship. The R will be a minus sign. But this is not a car data set. Are we okay? Right. So the LCC is found there. All right. Okay. It can be shown that values of R can only range from -1 to 1. I am not going to show it in this class because the math will blow your mind. Okay? It is quite difficult to show. It can be shown. R is trapped between -1 to 1. You cannot create a data set whose R value is going to be outside this range. All right? So remember that. Okay. So when you find that your R is -1, remember what I said? Minus sign just tells you that you have a negative linear relationship. But when it is the special value -1, which is the most extremely negative one you could get, this is called perfect negative linear correlation. What do I mean by perfect? So I hope this pen works. I'll draw you one. If you oh, it does. Okay. If you find that your points, not, see, I can't even draw a straight line. That's embarrassing. Okay. If you find, okay, first of all, do these points exhibit a negative relationship? Yes. If you find that not only they have a negative relationship, if you drew your best line, the line went through everything perfectly with no gaps. This is called perfect linear correlation. That's it. So let's do a very quick run. You also know that R can go all the way to 1. Anyone care to guess what is R equals to 1 called in words?
Perfect positive.
Perfect positive linear correlation. Good. We will get to that one in the chart. Perfect positive. And can you imagine what a graph would look like? It would be the same thing, but going in a positive direction. Yes. Yes.
Is it like if it's below 0.5, it becomes imperfect because it's too scattered?
No. Again, very good point. So can you get, okay, good. So can you guess? The next value of R I'm going to talk about is R is still negative, but large. So you can write in your slide, minus 0.8, something like that. Not quite minus 1, but not near 0 either. So let's say minus 0.9. What do you think that's the interpretation will be? Anyone care to guess? Your R value is close to minus 1, but not quite minus 1. Any guesses? Is it still negative? Yes. So you still have negative linear correlation, but the word perfect is going to be replaced with, what do you think? I'm thinking of a word that starts with an S.
Similar.
Very close. Not okay. Perfect is perfect, but this would be S T.
Standard.
Mm,
Stacked. Straight.
strong.
I knew that. So strong. That was my next step. Strong.
Good. Strong. Strong. What would a strong negative linear correlation look like? Well, you have points kind of like that, but not everything falling straight. Like, does it make sense?
Yeah.
Right? Strong. It's strong. It's just not perfect and strong. Good. What about a value of R that's still negative but kind of small and getting close to 0? What do you think?
Moderate.
Right? Yes, that's generous. Let's just skip that step. If R is small and negative, like let's say we give it a minus 0.2, right? Getting close to 0, this would be weak, right? And can anyone guess what I'm going to be writing in the next row? You see, we've gone from minus 1 to minus 0.9 to minus 0.2, and this one's going to be
0.
yes. So can you write R equals 0 in the next row? Anyone care to guess? If you get an R value of 0, almost right. What word's missing? No.
Linear.
Yeah. All right. No linear correlation. You want to make me happy? Say linear, right? It doesn't take much to make a stats professor happy, you know. Don't leave out your hats from a prediction equation. Say linear, things like that. Say statistically significant. These are some catch things that really make the professor happy because it means you understand what you're doing. All right. See, as I said, R is a measure of linear correlation only. You know why? If you have a set of points that fit exactly a circle, which can exist, do you know what the R value is going to be? 0. Really, that's an easy way to remember. The R value is going to be 0. Now, is it true that there's no correlation between this? You're going to be kidding me. There's a circular correlation. It says there's not a linear one. So that's why the importance of the word linear. This would yield an R value of 0. There's no linear correlation. Some other relationship exists. I mean, for example, not every relationship in life is romantic, right? You have a relationship with your dog, you have a relationship with your parents, you have a relationship with your friends. Not everything's romantic. So on a romantic scale, there's no romance. This is some other relationship, something like that. Measuring some other relationship. So our job is to measure the strength of a linear relationship. And that's all you can do, all right? Okay. Okay, what about R is small and positive? This should be quite easy. As you start leaving 0 and going towards 1, you can give an example. R is 0.2, something small but positive. What do you think the interpretation will be? Weak positive LC. That's right. And I think we'll just speed up over the rest. And we've already answered the one where R is 1. You have perfect positive linear image. Yes.
Would 0.5 be moderate?
So to answer your question, what's considered weak? That's a little bit subjective. I would say 0.5 is moderate. Not that strong, not that weak either.
Those are like 0.3 to 0.7 is moderate, strong and weak.
Yeah, I would say that's a good guide. Yes. Yes, actually, I like that. Right. But these are kind of subjective. So is there a statistical test for that? Yes, that's coming up. Right. Because that is kind of subjective, right? Like, is it cold in Holland? Yeah, relative to what? You see? It depends. If you're comparing it to like Siberia or northeastern China, or what, then no, it's not cold, right? But if you're comparing it to like the tropics where I'm from, oh yes, insanely cold, right? So, but lest we complain about how snowy it gets and all that. Having lived a long number of years in the tropical zone, it's not all it's cracked up to be. Trust me. Ugh, it's so humid. If you think summers here are humid, you ain't seen nothing yet, right? Okay, so the value R squared now, we're going to talk about R squared. We've talked about R. What's R squared? R squared has something which I think you cannot guess. So I'm going to give you the answer. R squared measures the percentage of variability in the response, which is explained by this model. It has a very nice interpretation. So in this data set, R square, I repeat it here in Jamovi, R square was about 50%. That's a percentage. It means this model, 50% of what's going on with your height is explained by your foot length. Does that make sense? Foot length tells you about half of what's going on with your height, which is actually pretty good considering how many things affect your height. Foot length in this model explains about 50% of what's going on with the height changes. So clearly, a linear model is superior. The higher R square is, the more the model explains. And R square that is low means the model is not telling you very much. So if any of you is doing a project in chapter 10, which I know some of you are, all right? And I'm very excited to see your results. Project presentation day is usually a lot of fun. I've really thoroughly enjoyed myself. Students do take projects seriously. I mean, there's the odd group there's the one or two groups that they come to the front like pulling teeth. They don't do a good job. But most students do a really good job, and I'm really looking forward to it. Don't be depressed if you do a study like this and you get a pathetic R squared. That's quite common. If you get a super good R square, I will be very, very excited for you, right? If you did, student projects tend to have very low R squares. You know why? Because usually the variables that you pick, they may be related, but they don't really explain a whole lot of what's going on. That's it. Again, can you get full credit for your project? Of course, analyze it correctly. I'm just saying it will be a cherry on top if you get an R squared that's pretty high. But don't be surprised if it doesn't happen. All right? Okay. Okay, now we come to the hypothesis testing portion of all this thing. Notice that we used little a to represent the y-intercept and little b to represent the slope. Where did these numbers come from? I know they came from the line. Where did the line come from? Didn't the line come from looking at those people's height and finding the best line possible? In other words, if I change the data, do I get different possibility of A and B? Yes. In other words, you give me a data set, I can find you the best fitting straight line. If you change the data, I'll get a slightly different line like that. So the slope and the y-intercept are what we call observed statistics. You don't directly observe them, but they are calculated from data that you do observe. Am I making sense here? The slope and the intercept are calculated by Jamovi from data that you feed it. That makes it an observed statistic, even though you didn't do it yourself. It comes from observed data, little a and little b. So you can guess, why am I using English letters for these two things? Because I get to see the slope and the y-intercept. Now I'm going to ask you to stretch your mind a little bit. Can you imagine, is there a population parallel of the y-intercept and the slope? What do I mean by this? Okay, I'm going to draw. This is the most fun picture to draw in the whole semester, right? See, the data set for the foot length had 20 people. There are 20 dots. Okay, I'm not drawing 20 dots, but imagine there are 20 dots. From these 20 dots are calculated the least square line. This least square line has a y-intercept called A and a slope called B. All right? These are observed because they come from 20 dots. Are there more than 20 people in this world? Yes. And the answer is yes. How many are there currently? 8 billion plus? All right. What would happen if I did this? Am I adding people to my data set? Okay, imagine there are 8 billion dots on the board. One for every person, living person. Right? Will the computer still be able to fit a straight line to this? The answer is yes. Do you think the line is going to be different? Yes. Where is that line? Okay, unfortunately, there's no other color here, so you're just going to, well, maybe the line will be like this. Is it still a line? Yes, but this is the population line. And therefore, every line, population or not, has a y-intercept and a slope. So we are really on a roll today. Can anyone tell me what is the symbol given to the y-intercept of the population line? Any guesses? Hint, hint, hint. This is called little a for the sample line. The population line, what's the symbol for the y-intercept? Very good guess. It's not big A, it's a Greek letter. What? Remember population Greek? Which is the one that we choose? This, okay, it's not mu, it's not pi. That will be confusing. This is A, so the population analog would be alpha. Yes. The slope for the sample line is little b. Any guesses on what the slope of the population line will be called? Yeah. Are you seeing the big picture now? Everything in statistics is like that. You have an observed proportion p hat. What's the population counterpart? Yes. Yes. You have an observed sample mean called x bar. What's the population analog? Now you have an observed intercept and slope, and the population counterparts are. Almost forgot how to write data set. See, this is like, as I said, this is like the last episode of a show that's going to be cancelled. Everything is reviewed. Now you can see it's all coming together. Greek letters represent numbers. These are all numbers. But you don't know what. Now, do I know what alpha and beta are? I don't, because do I have access to 8 billion people's height? No, I don't. But does it stop me from conceptualizing that these numbers exist? They do. Okay, so once again, the unknown long-run value of the y-intercept is a population parameter, and it is symbolized by alpha. The unknown long-run value of the slope is also a parameter, and it is symbolized by beta. What is beta in our data set? You will notice that it's very similar to our interpretation of B, but there is a slight difference. If you look at how I interpreted the slope from our original observed line, I said it is the predicted height increase in height. Notice now I don't say increase, I say change. And I put the word long run expected. These are things you need to write down in your slide. Interpreting the population slope is different from interpreting the sample slope. The sample slope is, that's the predicted rise in height for someone whose foot length increases by 1 cm. That part's the same. That increasing by 1 cm is the same. But the wording is slightly different. Because this is a parameter, the word long run must always be there. Is this okay? We'll get more practice when we do a worksheet, right? Which we don't have time for today because it will take me all of today's class to finish all the slides. All right? Long run change in expected height for a 1 centimeter increase in foot length. That's beta. Notice again, it's words. I don't know what beta is. I can describe it, but I don't know what it is exactly because it belongs to the population. Right? This is one of the more difficult concepts for students to get, I admit. All right. So we are not strangely, we are not so interested in alpha in this class. So you can actually write in your slides, not really interested in alpha. It's a thing, but we are not. We are only concerned with beta, the slope. All right. Can anyone guess, after all the time you've had with me, and this is chapter 10, what do you think the null hypothesis says about beta? Remember, hypotheses are always about parameters. That has never changed. And chapter 10, we are going to learn hypothesis about beta. Anyone care to guess? What do you think the null says about beta? Yes.
That it's equal to alpha.
Oh, that's a very good. Okay, it's not that, but alpha is not of concern in this class. That's a separate issue. It's a number. Can anyone guess what number the null says beta is by now? Yes, the null says beta is 0. Once again, 0. All right. Again, but all right. The null. Okay. Now there are again 3 possible alternatives, and that should not come as a surprise. Now, please just copy this down. There's so many things to catch on at the same time. I don't have time yet to talk about this one. Just copy that down. There's an equivalent one I must have. All right. Okay. What is rho? Remember the LCC I taught you about that measures the strength of a linear relationship? What was the symbol for that? Just maybe 10 minutes ago, we were talking about this. What's the symbol for the LCC? Give me an English letter, something you observe. R. Good. But is R a part of the English alphabet? It is. What's the Greek counterpart? Rho. Did you know that? Oh, the Greek R is rho. That's why it's called rho. Right? R. Right? The English alphabet came from the Greek, okay, not the other way around. So, in fact, you can think of some people write their R almost like that. It's not a P, okay? In fact, actually, Russian uses Cyrillic text, and this is their R. Right? That is why you can see this POCCI, Russi. That's right. It's ROSSI. Right? Anyway, what am I doing? All right. So, there was another color here. Okay. So, what is rho? Rho is the population counterpart of R. So, we also talked about little r. The population version of that is rho. What does it measure? It measures the strength of the linear relationship. So, it is equivalent. These two numbers are the same thing, but they tell you the same thing. Saying rho equals 0 is saying beta is equal to 0. What are you saying when you say that the slope is 0? Does anyone? Yes, a 0. Good. a slope that a zero slope means the line is horizontal. What does that tell you about the linear relationship when you have a horizontal line like that between two things? No, what kind of relationship? Yes, always remember, okay, no romantic relationship. Maybe some other relationship exists, but not a romantic one. So beta equals 0, which is equivalent to rho equals 0, is saying no linear relationship exists between foot length and height. Again, is that reasonable? No, I don't think it is. Are we going to probably reject the null hypothesis? Answer is we are going to reject, and I'll show you why. I mean, we can see from pictures that a linear relationship probably does exist between foot length and height, but the null always status quo, nothing exists. There is no such thing. All right. Anyone care to tell me what does beta greater than 0 say? That there is a, if beta equals 0 is no linear relationship, what do you think beta positive tells you? That there is a,
There's a positive.
yes, there is a positive linear relationship. And I'm sure once I've told you this, what does less than 0 say? That there is a negative linear relationship. What do you think beta is not equals to 0 say? That's a two-sided test. What do you think?
Is a linear.
Yeah, that there is one. We don't care about the sign. I really hope this is actually, yeah, because next after Thanksgiving we're just going to do some worksheets and all. This is the last class already, so I'm so glad everything's coming together. All right, so there is a linear relationship. That's what beta is not equal to 0 saying. It's a two-sided test, which you should be very familiar with by now. The p-value multiplied by 2. Same story again. So if you want to use a theory-based method to test these hypotheses, you need a statistic, right? Anyone care to guess? Do you think it's going to be Z or T? Yes, why? It is T. Why? Can you tell me why you chose T?
Because it's qualitative.
Quantitative. Yes. Because the data is quantitative. So you use this T statistic. Okay, let me explain the formula, okay? First of all, why am I putting a minus 0 here? Isn't it pointless? This is to remind us that, anyone know by now, why do I do this? The T statistic is, notice, estimate minus something over standard error. Why do you think I'm putting a 0 here?
Because that's the population.
Yeah, because what does the null say about beta?
It equals 0.
That beta is 0. That's right. There is an equivalent way to get the T. These two are numerically the same. I need to tell you both formulas because they exist in the wild. So you need to know. This is another way to get the T statistic. It's harder. This one involves R and also N. This one doesn't. This just means take B and you divide by the standard error of B. Okay, where do these come from? What's B? B is the slope. So 1.03 was your slope estimate. Remember 1.03? Anyone care to tell me what's the SE of B? Do you see it? This one, SE of B. Please ignore this number here. These are dealing with the intercept. We are not interested other than to know what it is. We don't do inference on alpha, so ignore these three. Just ghost them out. If you want, take your pen and draw a line through these three. It's not that it's wrong, but we are not interested in these. Don't cross this out. The intercept is important to get a prediction equation. Don't cross that out. But you can cross out these three. Don't read the wrong one. Okay. So you calculate the T statistic by taking the value of the estimate for the slope and you divide by the standard error. So if you, well, did I not show this? Yeah, I actually didn't. If you calculated B over the SE of B, if you take 1.03 and you divide by 0.241, You know what you're gonna get? Anyone care to guess? Don't use your calculator. Do you? This number is so important. Can anyone guess what it is without using a calculator? This is B over the standard error of B. What do you think the answer to this is? This is T. This is our famous T statistic here.
4.
Yes, 4 point. Yes, this number is so important. R calculates it for you. I said R, sorry. Freudian slip, right? Because I use R in every other class, not Jamovi. Okay, Jamovi says it's 4.29. Do you see the p-value less than 0.001 is reported as well? All right. This is for the default test in Jamovi, which is two-sided. Remember that. Jamovi gives you the p-value for a default two-sided test. If you want to do a one-sided test, what's the p-value? What is the relationship between the p-value of a one-sided test and a two-sided test?
Two-sided test 2 times.
That's right. A two-sided p-value is twice the one-sided, which means if you take the answer from Jamovi, you need to actually it's half it, right? The default is true. So if you want a 1, you halve it. Is this okay? Right? I know we're covering a lot of ground, but that's today's the last class already. So, and I really want to finish this before you go off on your break. And then after break, we'll revise by doing a worksheet and stuff like that. Are we doing okay so far? We've covered a lot, but the slides, go back, read the slides again, all right? How do you construct a confidence interval for beta? Okay, let me appeal to you once again. Haven't we learned how to make confidence intervals all the time? Confidence intervals are always constructed using the same thing. This plus minus something times something. Okay, I want a CI for beta. What do you think I'm going to put as my midpoint? Anyone? Yes. Last teaching class. You put a B here. Why? What else would you put? You want a CI for beta? Use B as your estimate. Yes. What comes next? Some kind of? Yes. And this comes from the T table. What comes next? Some kind of? You can give me words. Some kind of standard error thingy. Correct. Is it making sense?
Yes.
Haven't we done this like 10 zillion times already? It's just that sometimes this thing is not so easy. Sometimes this thing is a different formula, but the structure is the same. And so here, so no one has asked me yet. T table, is there a degree of freedom? Anyone care to guess what it is? Any good guesses? Okay, it's not 1. It's not 1.
N minus 2.
How did you get that? It's correct. Did I say so in the slides or not?
No, because usually the degree of freedom is at the bottom of every, like, is the denominator of the equation. For one of the equations you gave.
Oh, that is so good. So on the last class, okay, not the last class, but on the last teaching class, I was not expecting that. Yes, right. He saw this. That was very sharp. So overcome because I was not expecting. Yes, it's a curveball. It's M-2, not M-1. That was a very good catch. Yes, it was sneaky. It's there. Why is it M-2? I cannot tell you. It's beautiful, right? Linear model theory. I love it with all my heart, but I cannot tell you. And it's too difficult, right? It's the rank of the design matrix. Anyway, so well, it's n minus rank of design. Okay. Anyway, so All this that I've said is all here. Okay, so all is reviewed, and therefore here's the work for that. 1.03 plus minus 2.101 times 0.241. Now, I'm going to trust in the maturity of this class. I will not go to the T table to show you this. Is that okay? How many people were in this data set? I believe it's 20. So what's 20 minus 2? 18. So go to the 18 row, go find the multiplier. Have you done this like so many times already? So you can make a small note there in case you are studying on your own. This was the 18 DF multiplier. You might want to check that, right? If you are wanting to revise your multipliers, this is here because 18. Why 18? Because there are 20 people in this data set. This foot length data set at 20. How do we interpret this confidence interval? We are 95% confident that, do you see this thing? The long change in expected height for 1 centimeter increasing foot length. This long phrase is what? What's the symbol for the long change in expected height for 1 centimeter increasing foot length? These, how many words? 1, 2, 3, 4, 5, 6, 7, 8, 9. These 12 words or so can be replaced by one Greek symbol. What is it? Not B, very close. It's long run, so beta. That's beta. This is a CI for beta. Beta is a long run change in expected height. Yeah, long run change in expected height. Yes, for 1 cm increase in foot length. That's beta. And we are saying we are 95% confident that that's between beta. Do you notice? Does this CI cover 0? No. Why are we not surprised? This is a CI for beta. Did we reject the null hypothesis earlier? We did. What does the null say? The null says beta is 0. Did we reject this? We threw it away. So we are saying that no, beta is not 0. And that is why the CI did not cover 0. All right. Well, we are going to finish everything. I'm so happy. Right? There's only 2 more things to tell you about. Right? We have not talked about something that starts with a V. What do you think? Yes, our old friend, the VCs. What are they like? Well, the VCs are long, and so I have printed them out for you. I don't think, is this in your slide? Okay, good. We'll talk about them though, and I'll show you how to get the graph as well. There are 3 VCs that need to be checked. All right. First, all the people in your data set should be independent of each other. That's a very important VC. It is not checkable by drawing. You cannot draw the scatter plot and say, oh, these are independent. This is something you have to check with the person who gave you the data. Is it reasonable to conclude that the people in the data set were all independent of each other? So they can't like live in the same house or be connected in some form. This is a very important assumption that cannot be checked graphically. The other 2 VCs can be checked graphically. I'll show you the graphs that you want to see. All right. You want to see a plot of residual versus fitted. Fitted is predicted. Okay. You want to see residual versus predicted looking like this. If you have your slides with you, I want you to draw a straight line at 0 horizontal like that. You want to see your residuals occupying both above 0 and below 0 in a random fashion. You do not want to see a residual curve that looks like a residual plot that looks like this. This is very bad news. Like a smiling face. All right, like that. Here's your 0 line. This is very bad. You know why? It means, is there some trend in the residuals that you have not responded to? Yes. That means your model is bad. You have not picked up on a trend. Look at the residuals. It's smiling at you, right? There's a trend. You want a trendless residual plot like this. The other thing to check is what's called the normal quantile plot. This shows how closely aligned your data are to a normal curve. You want this plot to hug a 45-degree line the way this does. What you don't want to see is a plot that here's a 45-degree line. Your dots are kind of close in the middle, but then they kind of travel in a kind of an S direction away. Oh, this is bad. Right? The next step. You want it to hug the line. Is this okay? These are two graphs that you must know how to check. So you want to see things like that. So as I've said before, remember those infomercials? What sound do you make? Right? X. You want to see this? What sound do you make here? X. Okay, now this one, right? Are you still boiling your eggs the old way? Okay, that one, right? So X, right? You don't want this one, right? Another thing you don't want to see is a residual plot that looks like this. You know, like kind of like when people go to football games or sometimes they have this kind of blow horn thing. I don't even know if they're allowed to bring this. They're very noisy, right? Okay. You don't want to see residuals that are getting like fanning out and getting fatter and fatter like this. You know. Why? Right? Because this is a violation. This is a violation of what we call the homoscedasticity assumption. Well, huge word, so let me explain. All right. I'm introducing this word to you because for some reason business schools love it. And only business schools. No one uses this word outside of business school. And I'm aware many students end up in business school here at home. So I want to use this word. Homoscedasticity just means equal variability. So you don't get that smiling face, you don't get that blowhorn thing happening. What's the opposite of homoscedasticity? Anyone care to guess? Not a very difficult guess. No one knows? Homoscedasticity, the opposite is heteroscedasticity. Okay, so what's heteroscedasticity? Heteroscedasticity is when you have non-equal variability. So you have blowhorn. It's like that. Okay, that's not good for the kind of model we want. You want equal variability, homoscedasticity. All right. So last thing, and we're down to the last 2 minutes. How did I get these two plots on Jamovi? It is so easy. So let me show you. All you need to do is go down. Do you see assumption checks? Right? Scroll down on Jamovi, assumption checks. Okay. Anyone care to tell me what are the two things I want to check on? Residual plots. What's the other one? The Q, that's right. The QQ plot of residuals. And if you do that, you will see the graphs I produced and put in your slides for you. Do you see the QQ plot? The one that you must adhere to a 45-degree line and then the residual plot. Okay, which one to look at? Look at the residuals versus fitted, or if you put in your slides, this word is also predicted. That is actually it with 1 minute to spare. Thank you very much. I truly enjoyed teaching this class. Next week, when you come back after eating all the good food, we will do some worksheets on this chapter. We're not done a single one. And then we'll have project presentations on Wednesday. All right? Have a good Thanksgiving, okay? If you're traveling, stay safe, please. Right? Don't eat too much. Right?